Well, thank you very much, Myron. That was a great introduction. So today I'm going to be talking about mapping the beginning of the universe. And I usually like to start off a talk with a nice slide that really encapsulates everything that I'm going to talk about. But in this case, I decided to start off with something that I thought was a little bit cute and really overreaches. So, you know, if you're talking about mapping the beginning of the universe, you can ask all sorts of huge questions. And one can be, could there be anything outside of our universe, and could there be something before? And I don't really want to talk about that because that's a really hard question. But up here, you can kind of be inspired and know that we're asking a question that's maybe only one step before that. Right? So this picture shows some type of rendering of a landscape of lots of universes where each of these little bubbles is supposed to be a different universe that's just sort of hanging out. And I just really liked the idea of this sort of terrain. We're trying to figure out where we are on this and how our universe came to be and how it is the way it is. Now, I'm an experimentalist, so I'm not going to spend a lot of time talking about all the possibilities. I'm going to talk about specific possibilities and ones that are testable. And what I think is staggeringly beautiful is that we're actually at a point where we can come up with models that invoke physics 1 trillion times higher in an energy scale than we've ever observed with an experiment on this planet. Think about what will happen if you have that physics in the early universe, come up with testable predictions, and then go out and measure them. And so this talk, while it's right on the edge of asking these questions that are just amazingly broad and breathtakingly beautiful, we're actually at the point where we can test a lot of these ideas. And so that's what I think is really neat about this. So the goal for today's talk is that we want to understand what we know about the beginning of our universe, and not only what we know, but how we know those things. And really what that means is talking about theory so that we can get an idea of what could have happened, and then tying that in with observations so that we can actually get a handle on what we can rule out, right? It's great to come up with a theory, but what you really want to do is have the theory that describes the situation you're in. And that is what we're really going to do. Now, one of the key experimental tools we're going to use, I'm showing off to the right-hand panel of this, this slide, and it's the cosmic microwave background. And I'll tell you a little bit more about that later. And I just want to show you this nice beach ball that has what the cosmic microwave background looks like, and with the galaxy on the perimeter. We'll come back to that a little bit later, and I'll tell you a story about the first iteration of those, and specifically the instructions that came with them. Little foreshadowing. Okay, so before we get going, I just want to give you a quick tour of our universe. How can we know what began until we know what we have? So if you look up at the sky, with just your eye, this is a picture I took on top of a mountain in Chile where you're above 2/3 of the atmosphere. So you can see every star up there. I mean, it's the most beautiful view of the stars with the naked eye I've ever seen, except there's one catch, which is that if you're up above 2/3 of the atmosphere, there's not so much oxygen. And your body is really, really smart. It's much smarter than you, especially when you're at that altitude, because you just start turning off stuff that's non-essential. And so your eyes don't really see much. Because you could use that oxygen to survive. Although if you breathe oxygen, you can play fun games where you walk outside and you see black, and then you start breathing oxygen and you start seeing stars. But it's actually easiest to just take a nice big picture like this. But what's really amazing is that you look at this and you just get a sense of how vast the universe is. But when you actually go out and try to be a little quantitative and measure how far away the things you're seeing are, you find that they're only about 150,000 light years. Now that's, I've just to come up with a really sloppy analogy. It's like if you're standing in your kitchen, the house is the universe, it's like you just stand there. It's not going anywhere. This is just the tip of the iceberg. And you can really see that beautifully by taking from Hubble, where they just zoomed in on a dark patch of sky far away from anything. And this is called the extreme deep field. You may have heard of the ultra deep field before, but they decided to go even deeper than that. And what you find is that anywhere you look, you'll just find these galaxies that look a lot like ours, and there are just some beautiful examples in this picture that are extremely far away. And in fact, some of the objects that are in this image are 13 billion light years away, which is getting out to the edge. You know, if you've heard what the age of the universe is recently, you're getting really close to it here. Now, you can look a little bit farther, and when you do that, you see blackness. And that alone is really cool, because there's this idea called Olber's paradox, which says that if the universe was infinitely old and static, you'd expect there to be stars kind of everywhere. And if it's infinitely old, you can see arbitrarily far. So if you draw a line anywhere you point, you should hit a star, and the universe, or the sky should just glow as if the sun was everywhere. Now, of course, that's not what we see. And I think that in terms of communicating that the universe has a finite age and evolving, this is one of the easiest ways to see that. It doesn't require any difficult manipulation. It just is kind of there, hanging there. The fact that the sky is mainly dark tells you that the universe is evolving. But you can ask the question, is it really dark? And of course, to visible light, it is. But if you turn on microwave eyes, all of a sudden, it just glows. And I picked yellow arbitrarily because, you know, at the time that this light was emitted from the edge of the universe, the edge of the visible universe, it would have glowed like the sun. But the idea is that as the universe expands, the light gets stretched to longer and longer wavelengths, and it goes from being visible light that we would see to being microwaves that you need a special telescope to look at. Now, what's really amazing is that, you know, if you look back on the image of these galaxies, you see that the universe isn't uniform just a few 100 million years after the Big Bang. But when you go back to the scale where you're really only a few 100,000 years after the Big Bang, so this is the oldest light in the universe, and you zoom in on it, you find that there are little fluctuations, hot and cold spots, so it isn't totally uniform, but the amplitude of the fluctuations is only about 1 part in 10 to the 5. So the universe becomes incredibly smooth, but these variations are incredibly important because if you imagine having a universe that starts out perfectly smooth, not much is going to happen. Gravity tries to draw things in, but if you have a perfectly smooth universe, there's nothing to break the symmetry and you don't know where to fall, so you just sit there. And so if the universe didn't have spots like this, we wouldn't be here. So this, as I've said, is the oldest light from the universe. It's only 400,000 years after the Big Bang. And I just want to give you kind of a review and show you a different picture of what we just talked about. And so this is a nice graphic that I think is one of the nicest graphics to encapsulate the modern theory of cosmology that I'm aware of. And what it shows is it shows the history of the universe and all this stuff going from now over on the right side, and there they show an amazing telescope for measuring the microwave background called WMAP, which has now been superseded by the Planck experiment. And it looks back, and it looks through the local universe, just our galaxy to other galaxies, and then it goes back to the dark ages where no structures like stars had formed, and the universe was actually a pretty dark place for visible light. And then you get to the cosmic microwave background. And the thing we want to really talk about now is how we can learn about the very beginning, which came before that. And so, from this plot, you get an idea of how far back we're looking, but we want to figure out how we can push even farther. Now, one other point I want to make is that you can ask the question, what temperature is the universe? And you can ask it now, and if you do that, you find that it's about, a few Kelvin, which is minus 270 C. So in terms of extreme conditions, that's even worse than being at the South Pole. Yeah. And then you can run time farther back. And the key is that why is the temperature changing? Well, the universe, if it's expanding, that means that in the past it was more compressed. And if you've ever played around with things that expand, whether it's using a can of aerosol and you feel that the can gets cold as you deplete it when you're using it, you know that if you ran that process backwards and you compress a gas, it should get hot. And in fact, that's exactly what happens. And when you get back to the radiation left over from the cosmic microwave background radiation, which is what we saw in the microwaves, you find out that you would get something that's about 10,000 Kelvin. Or 10,000 Celsius. So it's kind of comparable to the temperature of the surface of the sun. And that would have filled the entire universe. And then what happens if you go back a little bit farther still? It should get even hotter. And in fact, you can, if you just take a naive model where the universe is expanding from some initial state, if you don't have any limit on how compressed it was, you can get arbitrarily hot. And in particular, high temperature means high energies. And so you can get to higher energies by just looking at the beginning of the universe. So in terms of trying to figure out what's going on with physics at very high energy scales, the fact that the universe went through this, expanded from this very compressed state means that you can probe potentially energies that are vastly higher than are accessible with modern particle accelerators like the new fancy Large Hadron Collider in Geneva. And so there's a huge opportunity to probe very exotic physics here. So the one thing we have to do, though, is that I've told you that the cosmic microwave background is the oldest light in the universe. And so the question is, how can we see beyond it? So we can't see past the CMB because the universe was ionized at that point, which means that light stops there. There's no way to see directly past it. But is there anything we can do to figure out what happened at the very beginning? Well, the great thing is that the CMB does carry patterns. And so what we can try to do is we can try to build a theoretical model of very exotic physics and taking known physics that we know had to happen. And then we can try to compare that to the observations we have and see what we get. And in particular, there's also new observations that you can make once you have a model to try to test this. And we're in this neat state where this is what's going on in cosmology, and we're at a point where we've tested some models, and then we know what measurements to make to test it further or potentially detect the smoking gun signal that will tell us about physics we think are there. So how do you build a theoretical model of the universe? You start with an empty pot. We're talking about cosmology, so you definitely need general relativity, which is just a theory of gravity. So, if you were sufficiently masochistic, one could use general relativity to understand trajectories of baseballs and things like that. So it's not anything more complicated than saying we need a theory of gravity to describe the universe. Quantum mechanics is something that you just can't avoid to doing physics. And then you need new stuff. I don't even know how to make a physical theory of I of Newt, so we'll skip that one. But you can come up with other things that are exotic that we haven't ever observed, like string theory. You can introduce new fields, which is really something that happens more often than string theory in these models, but both happen. And then take any good idea you have and throw them in the pot. Say an incantation, work really hard, do some calculations, and then arrive at testable predictions. Now, the key is that the prediction should be testable so that we should be able to go out and do observations and make contact with this theory. And then we're going to run it backwards to figure out which ideas that we introduced, whether they be I of Newt or new fields, make sense and are actually useful. So whenever you do this, if you start with a model, you have to make sure that it matches the observations that you have. And if we just think about the picture I showed you and just sweep a lot of stuff under the rug that are other details that you'd want to match, just at the level we're talking about for today, you have to have the universe start out at the end of whatever, your calculation has to predict that the universe ends up being very smooth. Because we saw that the cosmic microwave background is only, these spots on the cosmic microwave background over here only have an amplitude of 1 part in 10 to the 5th. So that's very, very smooth, right? If you were sanding something at your house and you got it that smooth, it would be incredible. And so you have to have something be very, very smooth. The other thing is that you have to predict fluctuations so that it's not totally smooth, because if you made it totally smooth, the CMB wouldn't end up looking right. And in fact, we wouldn't be here probably. And I think that's something we really want our model to include. And then you have to match all sorts of other stuff too. But for the purposes of today, let's just talk about those couple predictions. So as I said, the ingredients we're going to put in are general relativity, which is a theory of gravity, quantum mechanics, and then new physics. I should say this isn't just a general model. I'm talking about kind of a specific family of models right here, which is inflation, which is the the sort of most promising model for describing the features of the early universe. And this is really the thing we're testing. And what goes into inflation is general relativity, quantum mechanics, and then you introduce a new field, which is just, something, to be very crude, like the Higgs boson or something like that, but it's not that. I'm just saying it's the same type of family of things, but at perhaps a trillion times higher energy scale. And then you swirl the pot and put it all together and try to make predictions. Now, before I tell you a bit about this, I just want to make sure that we're kind of on the same page about what general relativity means. And I said that it's a theory of gravity, and that's completely accurate. But the really important feature for understanding how inflation works is that it's a theory that describes how the universe will expand. And so a generic feature that has to be in cosmology is that the universe is expanding, and that becomes incredibly important for describing what happens in the very early universe. The next piece that I really want to get across to you is quantum mechanics. And I think the easiest way to understand quantum mechanics is through the uncertainty principle. This is, I think, the only equation that I have in here. And what it says is that delta E times delta T is equal to some number. It turns out the number is really small. And so what does that mean? Well, delta E is how much the energy can fluctuate, and delta T is over what time period. And so what this says is that you can have a huge fluctuation in energy as long as it doesn't happen for very long. Or you can have a tiny fluctuation in energy that lasts a long time. And so what this means is that if you look on very small scales and look very carefully, you'll be able to see fluctuations in energy and stuff that you wouldn't necessarily normally expect to happening. But it goes away quick enough that it averages out and you don't notice it in everyday life. But when you really go down to small scales, this is a very, very important feature of our reality. So now let me kind of sketch what inflation might look like. So this is a cartoon guide. So if you just try to draw a universe, you could draw anything. And I don't mean draw. I mean if you try to pick what the laws of physics are, how curved the universe should be, there's just a lot of freedom, and it can get really messy. And so I made this thing that looks like paint that's completely messed up. But that's not how our universe looks. We want to make it very, very smooth. And so there's one way you can make it very, very smooth very easily. If you can just figure out how to make the universe expand rapidly according to general relativity, then you can smooth things out. So what you do is you introduce a field that causes the universe to exponentially expand. And so when it exponentially expands, it very quickly flattens out and comes to a very, very smooth state. And so that accomplishes one of the aims. And so that's one of the key predictions of inflation, is that it smooths out the universe irregardless of how it starts out, so that you end up with something that's nice and smooth and doesn't have any strange features to it and is spatially flat and other things that I haven't talked about today. But of course, that won't solve all our problems, because we have to be able to have the fluctuations that we observe in the cosmic microwave background. So how do we put those in? And that's where the second piece comes in, which is quantum fluctuations. So the way this works is that if you imagine a quantum fluctuation, and this is a cartoon guide, so it can be very cartoony, is that you could imagine a fluctuation where you have a little extra energy somewhere and a little less energy somewhere else. And that actually means that the density of the universe is changing. And so here I've drawn, red as high density and blue as low density. Now normally, if the universe weren't expanding, that would just go back to normal and you wouldn't see anything. But it's very, very different when you're in this rapidly exponentially expanding inflationary phase. And what happens is that you get a little quantum fluctuation, and before it can relax and go back to normal, it becomes frozen into the universe. And so you end up taking these quantum fluctuations and stretching them out to large scales. And the universe keeps expanding and keeps expanding and keeps expanding. And so you keep getting lots and lots of these quantum fluctuations that keep getting dragged to bigger and bigger scales. And at the very end of it, you end up with something where you have these fluctuations everywhere. And you end up with a universe that's nice and it's not very uniform, and it has specific predictions for what the spatial distribution of these fluctuations are. That it basically has roughly the same power on all scales if you look at it the correct way. The other thing I want to say, this is harder to draw, but it's very, very important because it's a very exciting thing that we can test, is that this is so violent that you also get gravitational waves generated by a similar mechanism. And so if you look at the end of this inflationary phase, you have gravitational waves propagating all over the place. And the neat thing is that they have an amplitude that is dependent on the energy scale of inflation. So if you can measure these gravitational waves, then you can learn about the energy scale of inflation and really start putting handles on where new physics is happening, which I think is really one of the most exciting things about this field. So then, obviously, those fluctuations that I just showed you are at the end of inflation, and that's roughly at t equals 0, maybe 10 to the minus 30 some odd seconds after the beginning of the universe. And so then there's still 100,000 years between this pattern and the pattern of the cosmic microwave background. But the great thing is that these are small enough fluctuations that over those 400,000 years, they grow from very, very small to 1 part in 10 to the 5th. And so you can take predictions from an inflationary theory that predict these quantum fluctuations and the sort of density perturbations and gravitational waves and run things forward to get a simulation of the cosmic microwave background. And then if you compare that to your observations, then you can learn whether or not your theory makes any sense at all. I just want to say that this map here comes from the Planck satellite, and it's actually real data. So I'm kind of cheating a little bit because I was saying that this was a simulation, but really it's the real data. But you can make simulations that match it, and I'll tell you kind of how that works in a little bit. But there's another thing, which is the polarization. And if you look in the background, I'm showing these temperature fluctuations. So the background's supposed to be hot and cold spots, similar to what the previous picture was. But then we have all these little arrows that show the direction that light is polarized. And do those look complicated? Yeah, right. It looks kind of hairy and disheveled, and like there's a lot of work to do. So there's great math tools for doing this. And the way it works is that you can decompose it into different types of patterns. And we call those the so-called E mode and B mode. And if you look at them, the E mode kind of goes radially out or only around, and the B mode kind of has a little bit of skewness to it. And there's a really neat thing, which is that the density perturbations make E modes, but no B modes, and gravitational waves make both. And so if you can detect the B modes, then you can actually measure the gravitational waves that were propagating through the cosmic microwave background when it was emitted, and it gives you a direct way to measure gravitational waves in the sky. And frankly, that was exciting enough for me to want to go to grad school and study this. I just thought that was amazing. And what's really amazing, though, is that as I learned more about it, I found out that the fact that they were gravitational waves was only a little bit interesting compared to the fact that these are gravitational waves that came from quantum mechanics at this energy scale that's unreachable by any other technique that I'm aware of. And for that reason, these B modes, if you detect them, I think can rightfully be called the Holy Grail. I don't know, does that look grail-shaped to you? OK, so we have our testable predictions, and now we have a way to compare them to observations. So in what I want to talk about for the second half of this talk, I want to talk about where we stand with comparing to observations and where we're going in the near future. And making these observations a reality is what I spend most of my work week doing. And so I'm going to spend a little bit of time talking about new technologies and new instruments that we're putting in the field right now. So first, I want to tell you about the sort of state of the art for constraints. And I could rightfully put the Planck satellite up here, but I'm also insanely proud about work I did on the South Pole telescope. So I want to talk about this. And actually, we managed to get constraints on inflation that are not too different from what Planck managed to do from space. So this is the South Pole telescope. Do you guys recognize what the weather pattern is in the background? OK, so I heard sundog. So I'm a Californian, and I'd never seen anything like this before when I went to the South Pole. I mean, these are just gorgeous, things that come from different shaped ice crystals. So you have things that are planar, and they settle down like this and make the bright spots on top. You have sphere-like ones that make the big kind of circles. And then you have needles that kind of settle down at the edges. And you end up with these just beautiful patterns. And if you look at this on a slightly a screen with a little bit more color range, you can actually see that there's another ring beyond that. And this is, I think, the best picture I've ever taken in my life, so I'm just going to dwell on it because I don't get to show it that often. But right there in the foreground, there's the key piece that is more important for this talk, which is the South Pole Telescope, which is a 10-meter telescope that we built about 1 kilometer from the South Pole. And this is an example of one of the maps that came out of it. And this is the cosmic microwave background, and of course you're seeing some whitish dots. Those are active galactic nuclei. So, you not only see the cosmic microwave background that's the kind of key thing that you want to see, you also see some stuff from the recent universe that, if you're an astronomer, can be an amazing signal, and it depends what you're interested in. I personally would rather look at the cosmic microwave background most of the time, but it's actually really fun to be able to do a broad range of science. So if you take that map and then you do some math to compare it to inflationary predictions, what you end up with is something like this. And there's some arcane numbers or names for the axes. There's NS and R. And for the purpose of this talk, let me help you understand what they are. So NS tells you something about the shape of the inflationary density perturbations. What it's really telling you is, the model I sort of showed you alluded to the fact that the fluctuation should be about the same on any scale. But if they were exactly the same on any scale, then inflation would never end. Right? It would just go on forever. So something has to give. It has to start sort of ramping down towards the end. And so the NS is a way to encode that, where 1 would be perfectly uniform and less than 1 would be inflation that can end. So if you look on the constraints, and there's various combinations of WMAP data, which is all sky and low L, SPT data, and then also combining the CMB with other measurements of cosmology, what you see is that especially look at the blue curves, we rule out NS of 1, which is really consistent with inflation, right? Inflation has to end, so that's a really powerful measurement. So it says something like inflation really is supported. The other axis is R, which is proportional to the amplitude of inflationary gravitational waves. And there we don't have any detection, but that's, I think, one of the most exciting axes in this plot to look at, because it says that we can actually constrain and rule out some models. Now, there are a bunch of dots back there, and those tell you, those are different models that people have come up with that seem perfectly reasonable. And the great thing is that if you look at the black dots, there's no way that's happening. And so that's a model where you take perfectly sensible physics, you can almost explain the whole universe or the beginning of the universe, and now you can completely rule it out. And so we're at a point where not only can we support many of the features of inflation, but we can also rule out many of the models of inflation. And so when people first started discussing this theory, many people thought this would never be experimentally tested, and then here we are, just about 30 years after it was first proposed, and we're actually at a point where we can falsify models, and there's a chance that we might even be able to hone in on them and really get an idea of what's going on early on. Now, of course, you always need a better instrument, and the one that I'm working on now is called ACTPOL, which means the Atacama Cosmology Telescope Polarization Experiment. And this sort of strange structure here in the foreground, which is, very, very tall. If you look, there's a fence around the outside edge that's about 10 feet tall, so it's a very tall structure. That encloses the telescope. And the reason that you have a structure like that to enclose the telescope is that this is at 17,600 feet in Chile, and you end up with high winds. And you really don't want rocks and things like that blowing at your telescope. The other thing is you want to reflect any stray light that would hit from the ground up to the sky, so that you can really get to these very faint signals. And so what ACTPOL is it's a new receiver for this telescope comprised of three independent detector arrays, or it's kind of like 3 cameras, that we've deployed, and we're going to do a lot of different science goals, but the one we will put better constraints on inflation, and the main way we're going to do it is through polarization, because at this point the temperature has been measured almost as well as you can ever do it. Just to be a little bit technical, this is what one of the cameras looked like, and what we found was that on the bottom left, you see the telescope, and this is a ray tracing diagram, so you see how the light kind of goes through the primary mirror to the secondary mirror, and then down into a camera, which we zoom into on the right-hand side. And the camera consists of a couple things. You have these lenses that correct the light and make a nice image, so it's just to make a good image down to a detector array. And you may just think lenses, detector array, this is something you go buy off the internet and then you just put it together and you're done. But the thing you have to realize is that at the millimeter wave, these are new technologies that have never been used before. And so all of this stuff is a major research, could be engineering research if we were in engineering, but the point is that we really care about measuring the cosmic microwave background, so it's the thing that we have to solve to get our job, to get the data we want. And so what we found that's kind of interesting is that we couldn't make this work without using silicon for the lenses. So we actually take silicon from the semiconductor industry. They grow it into these big, they're called boules, but big chunks that are like this big in diameter, and we make our lenses out of that. Now, one of the difficulties of using this as a lens is that, does that look like a metal? Yeah, so that's actually silicon, and it's 34% reflective per surface if you don't do anything about it. And so that obviously doesn't look like a really bright idea. But the thing is that if you can solve that reflection problem, all of a sudden it's almost the best material you can have, because it's basically lossless and allows you to bend light the way you need to. But what's really hard about that is that not only do you have to solve that reflection problem, you also have to solve it where where you're going to cool these things off to a Kelvin, or minus very, very cold, which means that if you didn't do it right, they would break in half when the coating and the lens contracted differently when things get cold. And so we came up with a really neat solution to this at Michigan, which is to cut features smaller than a wavelength into the surface to make the reflections go away. And I'm just showing you roughly what those features look like on the bottom left, where we want to take a saw and cut these little tiny features into this basically glass. It's not really glass, it's a single crystal. So it's a really tough problem. Now, since we're at Michigan, we should be really good at manufacturing, right? I don't know. I feel like that's maybe morally what we're doing. We're carrying on the great traditions of being really ingenious in making stuff. And so you'd think that you could just use a silicon dicing saw, but the silicon industry only does things that are flat, right? You don't have curved chips, and so we're doing something that's very, very strange. And so we built our own machine to do it. And there's my grad student, Charles, who actually built the machine. And when we put this together, we managed to make these lenses that effectively let all the light through so that you can make the telescope work and get the data that you need. And this is a picture of one of the lenses. You can zoom in, and we managed to cut kilometers of these micron-accurate posts to make the light do what we need to get our data. And this thing on the left isn't a model. That's actually an image that we reconstructed using some really fancy stuff that we have at North Campus. Now, after you've done that, then you have to get the light into detectors so that you can actually image the sky. And this is what one of the detector arrays looks like. It has 512 pixels. And does that sound like a lot? No. Well, in 2000, when I worked on my first experiment, we had 1 pixel. In 2004 and 5, when I did my thesis experiment, we had 16. And so this is actually following Moore's law, more or less, where we're just going to more and more pixels. And you can't tell. This looks like it's just like a metal thing that we made, but this is actually made out of a bunch of silicon wafers that are stacked and plated. It's just absolutely beautiful engineering. And this is the team that put that array together at Princeton. And so then you just combine the lenses, the detectors, put them in a cryostat. And if you look, that cryostat has all this funny paint on it on the right side. It turns out that what we had is a competition called Articama, where we let artists propose what art they wanted to put on our camera. And then we paid a company that makes auto decals to make it, and we wrapped it. And so when we deployed our instrument in Chile at 17,000 feet on the ACT telescope, we not only have a very high altitude CMB experiment, we also have one of the highest art exhibits in the world. So then you can turn the thing on, and we've been observing for something like, I want to say about 90 days at this point. So we're really kind of fresh into the observations. And what you want to do is you want to make sure that you actually have an instrument working. And so we pointed at this supernova remnant, which for the purposes of cosmology maybe isn't that interesting. But what's great about it is it's very polarized. And so if you look at the upper left, that's what the intensity looks like. So you see a nice little blob. And remember, we're a microwave telescope, so you wouldn't expect to see lots of detailed structure. It's not quite as beautiful for looking at objects as you might get with an optical telescope. But then if you look in the bottom right, that's the polarization that you get out of it. So we actually have this nice polarimeter that's sensitively making maps of the cosmic microwave background. So at this point, there's this great thing that happens in particle physics where you turn on your experiment and you can do the last generation of experiments incredibly fast. And it takes a while to get to your new thing. That's how you always design experiments. You design them so that they're more sensitive, so you can do what you would have done 5 years ago incredibly fast, and then move ahead to the new measurement that's state of the art now. And just using a small amount of data, you can actually map the cosmic microwave background with ACT already. And when you do it, you get an image that looks very consistent with other things we've seen, and in fact would have been state of the art just a few years ago. And we're just poised right at this point to push farther, and in the near future we'll be able to start making polarization maps and pushing back our understanding of inflation, and then also pursuing a lot of the other science that's on this in this picture. So all right, I think I have inadvertently run a little bit short, so I'd like to just answer any questions you have about everything for as long as you want me to answer them.